All right, so we are on the mic, okay? I'm taping this during period 9. Sit down. We're doing the lesson. I'm taping this because there was a lot of people missing for the AP World exam. So take out your homework. The first question was question number 3. So it was on linear regression, so quickly check it because we need to go through this. The packet is in the back there. Okay? So, shh, I am taping right now. Your homework's got to be out. Yes. Andrew, sit down. Let's go. All right, so check your answer to number 3. It was a linear regression. Here's the line of best fit. Okay? Then it said to, I think it said 2020. Yeah, so number 3, you had to, they said, where is number 3? Okay, number 3 was the practice problems, and then it said you had to predict for 2020. But since it was since 1990, that's 30 years later. So you had to plug 30 in. Okay? Then you get approximately 5,058 students. They said, what are the units of the slope of this linear model? So it's change in y over change in x. So that's change in population over change in time, which is students per year. And basically what the slope represents is for every additional year, on average, the population is going up about 52 students. Okay, so that was 3. What's up? Because it said 2020. It's since 1990, so it's 30 years later. Yes? Okay. The next one was an exponential regression. So you had to plug in list 1, list 2, and actually run the exponential regression. Now, hold on, I'm just going to pull up my calculator. That takes a while. All right, so when you do the exponential regression, and again, I did this quickly yesterday at the end of the period, you get this. So you have to plug in your A and your B, and it said to round to the nearest hundredth. Okay? I see a lot of papers blank here. Oh, you did the wrong ones? It was a practice problem. We did do this. It was at the end, whether you guys were paying attention or not. Oh, you were trying to do the sign regression then? Oh, okay. I think I'm just gonna make a little video of the sign regression because the idea of it, I mean, it's probably not going to be on the Regents, and I want to go through I want to finish that packet and start review. So I'm probably just going to make a little video on the sign regression. You guys can watch that. Well, you plug list 1, you plug 0, 1.5, 3, 4.5, and 6 into list 1. Then you plug 5.3, 3.1, 2.4, 1.6, and 0.7 into list 2. And then you run the exponential regression. Yeah, you have to read it. It says exponential regression. Then it says algebraically determine the time. Oh, the actually important thing here is they said time. They had, like, actually this is Kirk's answers right here, but he's wrong because when they give you different variables for the x and the y, you have to put those in. So they put for the y, they put I, and then for the x, they put t. So your formula has to be in terms of those letters. Okay? Now, part The second part of the question says, algebraically determine the time until the rate reaches 0.25 inches. So you have to set this equal to 0.25. Now, how do we go about solving this? Yep, divide by 5.47. And then, yes, excellent. Hold on 1 minute. I can't write that fast. All right, so then remember, whenever we're solving for a variable and we have to bring it down, we have to take the log of both sides. Remember that? Guys? Okay. So, oops. You take a log of this side, and then you take the log of this side. What happens to the x? Where does that go? Yep. So you divide by log of 0.73. And then you get x equals whatever this number comes out to be, which should come out to be 9.804. Dot, dot, dot. And to the nearest tenth would just be 9.8. Oops. Okay. All right, so those were the practice problems, but now let's go to the Regents questions, which are in the blue packet. So the Regents questions, we started with number 14. So go to number 14. Hold on a minute. No, it's fine. I just wanted to make sure it was still recording. All right, 14. So what did you guys put for this choice? Yeah, okay. So which ones did you know it wasn't? Yeah. Okay. Definitely not 1/4. Now, remember with exponential regressions, exponential functions rather. These are your y-intercepts, right? And these are your rates of growth. So what is this one growing at a rate of, number 2? What is that growing at a rate of? 43%. And then what is this rate of growth? 4%. So now is 43% pretty big growth? Yeah. So like if you look at the function, the y-intercepts could both be these, right? But does this actually, is it growing by 43%? Probably not. So like, it's not. The answer is 3. Yeah, that's what I want to show you guys. So what I want you to do is everybody take your calculators out because we're going to need them today. Okay? Now, what we could do is we narrowed it down to these two functions. So what we're going to do is plug these into our y equals and then put the exact window that they have. So I already did this in period 1. So put these in your y equals. Everybody have their calculators? No. You should have your calculator. Okay. Yes, Ark. Yes. I'm going to talk about that today too. If your plots are highlighted, so if this is a black box and it's highlighted, that means you can't graph like normal functions, and that's only because we turned our scatter plots on yesterday when we looked at the scatter plots. So the way to shut them off is you can unhighlight it by hitting enter, or you can do second y equals and turn them off there because we turned them on yesterday and then you can turn them off. Okay, so we'll quit out of that. So put them in the y equals, and then what window should I use for this one? Yep, 0 to 100, and what are they going up by? 20s. Yeah, and then you hit graph. So you could see this is the one that's growing at 43%. Yeah, and this one is growing at the 4%. So the answer would have to be which one? 3. Yeah. And now, just to save time, you can, for question 15, you can do that same approach. But before that, which one of these could we eliminate just based on what it looks like? You mean because the rate of growth is so high? Yeah. No, I think 2 is the answer. No, I was saying it's the answer. Yeah, 2 is the answer, yes. But why can I eliminate 4?
Oh, because that would be declining anyway.
Yeah, this is decay, right? Is that showing growth or decay?
That's showing, the graph is showing growth.
Growth. Yeah, so this, you can eliminate this. And then, yeah, I agree with you. Number 3 is a really high growth rate, so it'd probably be one of these, and number 2 works. And you just do the same thing. Plug this into your y equals, set your window, and you can see that the scatter plot matches. What? Yeah, it does. Very high, yes. I know. I know, process of elimination, you could probably have gotten that it has to be 2. All right, so now the next question that we did was question 35. So how do we do this one? Explain it to me. What do we do here, guys?
Put all the data into the then.
Yeah, so let's do this one quick. Read me the data quick.
For L1, 0,
Uh-huh.
0.5,
Okay.
1,
Okay.
2,
Okay.
3, 4, 6.
All right, let's go L2. Okay. Oops. All right, go ahead.
4, 10, 15, 60,
Oops, 60.
260,
260.
1,130,
1,130.
16,380.
16,380. Okay. All right. Plug it, list 1, list 2, and then where do we go? Stat? Calc? Yeah. Yeah, we go to exponential regression. And this is just like we talked about yesterday. List 1, list 2. Frequency list is always going to be blank. The regression equation, you only store that if you want to see it in your scatter plot, but otherwise you don't need it. Yeah, for regressions, it's always blank, but not for finding like means and standard deviations. All right, so rounding this to the nearest whatever, what are we rounding it to the nearest? 1,000? What number is this again?
35.
35? All right, hold on, I just want to get to the right page. Okay. So we write it down, and what's my rounded equation, guys? 4.168, good. 3.981, yes. Yeah, and you can easily just read that from your output of your regression. Okay? And, okay, then it says, the researcher knows that people are likely to suffer from food-borne illnesses if the number of spores exceeds 100. Using the exponential regression equation, determine the maximum amount of time to the nearest quarter hour. Do they really have to do that? Nearest quarter hour? I feel like kids know how to do this, and then that kind of confuses them a little bit. So what do you have to do to actually find x? Yeah, we're going to put 100 into y because spores is y, right? And then what are we solving for? X. Okay, now what do we do?
Divide by 4.1.
And then I got on here 23.9. You can. 23.92, and I'm just going to go dot, dot, dot. I would have carried all the decimals. And now what do we do?
And then you take the log of both sides.
Yep, we're going to take the log of both sides. So log of this equals x log 3.981. Good. Divide by 3.981. Then x equals, I get 2.30?
Yes.
Okay, so now, yes. Log of 3.981 of this equals x? Yes, you totally can. And then use the log base key in your calculator? Yes, if you prefer that, you can do it that way. All right, so now to the nearest quarter, of hour. What's a quarter of an hour? 0.25. So it's 0.25, then the next quarter would be 0.5, then the next quarter would be, and then you're rounding up to the nearest minute, right? That's also 15 minutes, right? So 30 minutes, and then 45 minutes. So if I get 2.30, what's the nearest quarter? 2.25. So the answer would be 2.25. Or you could write 2 hours and 15 minutes.
What are you counting by? There you get.
You get 2.30, but you have to round to the nearest quarter, which I don't know.
Oh.
Yes.
I felt like that wasn't the right answer because it was asking for the maximum amount of time that it could be kept safely. But when it hits 2.25, then it's not safe.
Are you sure? Did you check it? Did you check? Like when you plug this in, if you do 4.168 rate times 3.981 raised to the 2.25.
Oh, if you raise it to 2.3.
Yeah, maybe that's why they said round it to the nearest quarter. Oh, really? If you do that again?
What if you don't simplify it?
Yeah. Yeah.
Could you just put in your y equals to 6 and then see when it gets to 100?
You mean like the graph itself? You could, but doesn't it say solve algebraically? Using the exponential regression equation, so you have to use the equation. Yeah. All right, let's do the last one on here, which was 36. So 36. Now, you have an A and a D. What is that?
Just like 2.
X and Y. Yeah, this is X and Y. So, what should your equation be in terms of? A and D. I would have gotten -1 because I broke I and X. I would have gotten this wrong. I mean, not if I was taking my regents, I probably would have, but I was doing it quick and I didn't read quickly. I mean, carefully. So you have to read carefully. So it should say D equals. Okay. Now, when you run the regression again, list 1, list 2, exponential reg, you get. You tell me, what did you guys get? 1.223. Yes.
Times 2.652
Yes.
to the A.
A. Okay. Now it makes sense, Lily, why you said you didn't understand because you were doing the sine one. All right, I'm going to do a little video on sine, and you guys can watch it. It will be like a 5-minute little video. It's the likelihood of having a sine regression come up is very slim. So I want to spend more class time now going into the last topic. So you know all the questions that we didn't do in the blue packet, we got to do them, and they all revolve around statistical inference, which I'm gonna warn you now. I'm going to talk a lot and explain a lot right now, and you got to listen. And I know that it might be a little dry because I'm lecturing, but you have to kind of set up the framework and for order for you guys to understand this. So hold on, I'm gonna give you these handouts. All right, ready? All right, statistical inference. A parameter is a fixed number of. Oh, first of all, before I even start this, what do you think inference is? Okay. What verb comes from inference? Infer. And what does infer mean? To guess or to. Based on information, what are you doing? Yeah, predictions or drawing Conclusions, yeah. So we're actually going to have data, and then from the data, we're going to draw conclusions, hence statistical inference. So we start off with defining what a parameter is versus statistic. So I'm just going to read these, and then we'll write some notes. So a parameter is a fixed number that describes a population, such as a percentage, proportion, mean, or standard deviation. In reality, we do not know these numbers because we cannot examine the entire population. A statistic is a known number that describes a sample, but it can change from sample to sample. Okay, so basically what's going on here is you have samples, and you guys should write this down, whatever I write down here, because these are going to be your notes. Samples based on means, and we have samples based on proportions. Okay, so if you have samples based on means, what's another word for mean? Yeah, average. So the parameter is known as mu. Now mu, spelt mu, is the population mean. Population mean. We don't know what the population mean is, and that's the whole point. Parameter is equal to mu, the population mean. Parameter. So we don't know what the population mean is. So what do? We draw a sample from the population, and we try to make conclusions based on that sample. So the sample mean is known as the statistic. Statistic. And that, as we have seen already, is called X bar. And that's the sample mean. Okay? So population parameters, sample statistics. So we don't know what mu is. You don't know what mu is, so you take a sample and you try to use the sample to estimate the parameter, so the population mean. Okay? It's X bar, which is the sample mean. Okay? Then you have samples based on proportions. And what's proportions? Fractions, and fractions we usually convert into decimals, which then can be converted into percentages. Good. Yes. Okay. So the parameter for sample proportions is P, the letter P, and that's the population proportion. The statistic is known as P hat. It literally is P with the hat on it. And that's the proportion, sample proportion. So just take this class. Your like samples based on means. It could be like how many texts every kid sends during my class. Could be a sample. Yeah. And then sample proportions could be how many people play sports in my classes. So you're taking like a count and then converting it to a percent. So the idea is that you don't know, you can't possibly get everybody in the population. So because we can't get everybody in the population, we take a sample. You're going to have to go quicker than this, Philip, because I got to keep going. Okay? So we don't know the entire population. We can't actually survey them all. So we take a slice. And we hope this slice is representative of the population. So we have to randomly collect the data. It should be unbiased and basically a mini population. So this slice of pizza represents the whole pizza pie. Okay? All right. Any questions so far? I said it's going to be a little dry because we're doing lots of definitions right now. Yes.
Like a study of the population is called a census, correct?
If you can survey everybody in the population, yes, it's called a census. Yeah. All right. So now on to this slide. Okay? So flip your pages. Okay? All right. So just a little recap here. For sample means they're averages. The population mean is mu. And the population standard deviation is sigma. And we've seen this already because we did this when we were talking about when we were looking at one variable statistics. So these are the parameters. The sample mean is x bar and the sample standard deviation is xs. xs. These are statistics. Okay. So again, and you're going to hear this over and over again, we do not know the mean of the population. So what do? You take a sample. So from the population, we take a sample and we average whatever I'm looking at here. I'll take the average of the sample, and that will be the x bar. Now, if I took an average from the sample, if I took a sample from the population, where do you think this sample mean would lie on? Do you guys have this? Do you have this line here?
What line?
No, you don't have this curve here, do you?
Yeah, we do. Oh,
You
we
do?
don't have it at the bottom.
Oh, I didn't want it to be there. Darn it. I thought I got rid of that. Shoot. Pretend it's not there. Well, actually, I can't do that now. But anyway. All right, so where do you think this x bar would be? So if you took a mean of the sample, where do you think it would lie? Yeah, it doesn't make sense that if you took the mean of and if supposedly it's a good sample and it's representative of the population, wouldn't the x bar lie right there? Yeah. Now take another sample. That's a mu. So now take another x bar. Yeah, he's right. Now take another x bar. Where do you think that one would stack up?
Hopefully on top of it.
Yeah, probably on top. And I take another sample. Where do you think that one would stack up? On top. Now, could you have, just due to people from like different subsets of the population, maybe they don't stack up where the true mean of the population lies and maybe they're a little far out? Yeah. Could it be far out on the right side, far out on the left side? Yeah. Could you have one here? 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 So what's happening right now? When you take sample after sample after sample after sample after sample after sample from the population, majority of the sample means are going to stack up where the population mean is, which makes sense. But because you're taking different subsets of the population, you're going to have variation in your x bars. This is known as sampling variability, what I have right down here in green. So as you keep creating samples, what curve starts to emerge? A normal distribution or the normal curve. And that will always happen. And I actually didn't want that line to be there. I wanted to erase it. And then you guys tell me, but it's okay. It's fine. All right, so now that's sample means. But what about sample proportions where I'm actually looking at percentages? The population mean, that's the parameter P. And the statistic is the P hat. So instead of mu and x bar, we have P and P hat, but it's the same concept. Okay? The standard deviations we're not going to cover in this course because it's a little bit more complicated of a formula. And you can do all these questions without knowing the formula. But if you take AP Stats, you'll know the formulas very well. All right, so now, again, we have a population and we don't know what the true proportion is. So since we don't know what the true proportion is of the population, what do you think we do? We take a sample. Instead of an outputting an output, p hat. Yes, exactly that. And then I'm going to, oops. Where do you think that p hat will lie? Yeah, on top of where the true proportion of the population lies. And then I'll take another one. And where do you think that one ends up? Probably on top. Are most of them are going to stack up on top? Yeah. And then again, due to sampling variability, what happens is you get a bunch of different p hats. And what curve are they creating? A normal curve, a normal distribution. That's what I wanted you guys to draw in, but the other one was already there for you. Yes, Jackson, go ahead.
The way we're learning it, like, so the way we use this information is because we don't know the population, we can't know that we're putting it on top. So we have to take multiple samples, like a large sample, and then make our conclusion from that, what the population actually is.
Well, so what happens is you hope that your sample is unbiased and like basically a mini representation of the population. Yes. And so you put a lot of emphasis in that sample. That's why it's so important to collect data. And like the ways of collecting data has to be random and it can't have any bias. And you have to really scrutinize your data collection method. So that one sample is where you assume the true population lies, like the true mean lies or the true proportion lies of the population. And then so what happens is as we keep, this goes right into our next slide. As we keep repeating this sampling, right? This is a type of simulation. So taking X bar after X bar after X bar and taking P hat after P hat after P hat, you're simulating what could happen. And computer programs do this for us. Our calculator is actually going to do it. We're going to do it today. So what happens is we get this normal distribution, okay? Now, this is where we actually draw conclusions. In a normal curve, 2 standard deviations out, what percent of the curve is within 2 standard deviations? 95. And we talked about that in great detail when we talked about the normal curve. Now, did we also say that if we're within 2 standard deviations, that that's likely to happen? Yeah, most of your data falls within 2 standard deviations. So we're going to say that's likely to happen. Okay? Now, if I got a p hat or an x bar that's outside of 2 standard deviations, is that unusual? Yes, very rare. There's a small percentage. It only occurs 5% of the time and 2.5% in each tail. So this is where we start to draw conclusions. And not only do we draw conclusions, but moving on to the next slide, we create what's known as a confidence interval. Okay? Now, write this down. A confidence interval estimates where the true mean or proportion of the population, yes, lies. And we're only going to do 95% confidence intervals, okay? So what that means is we're going to get a p hat or an x bar. And based on that p hat or x bar, we're going to say, okay, that's right smack in the middle, the p hat or the x bar. But we're going to do 2 standard deviations out. So you're going to do 2 standard deviations out to the right and to the left. And we're going to create a 95% confidence interval. What that means is that I'm 95% confident that the true mean or the true proportion lies between that width. So you kind of estimate where it lies, okay? Now, the margin of error in this course is always going to be 2 standard deviations. So whenever we see the word margin of error, that's 2 standard deviations. Now, that makes sense, margin of error. you're comfortable with being, you're comfortable with the margin of error of 2 standard deviations to say, if it happens in here, it's likely. If it happens in the tails outside of 2 standard deviations, it's unlikely. And then we're going to make decisions. So if you get a p hat or an x bar that's out here, this is unlikely to happen, and therefore your findings are going to be known as statistically significant. And same thing here. If you had an X bar on this side, your findings are unlikely, and therefore it's statistically significant. Now, I know we have to piece all this stuff together, and I know that you're going to probably, you might even want to rewatch this and to kind of wrap your head around this. But when we start doing questions, this will all make sense. So what we're going to do right now is a really fun, it's fun, I think. It gets you going and starts trying think about what's going on here. We're going to do a little simulation. So you guys all need your calculators out. You got to participate in this because I need your data. And I'll do one too. All right, so it says, if I toss a coin 10 times and I get 10 out of 10 heads, does this seem likely to happen? No, right? What would you expect to happen? 5 and 5. And how'd you get that? It's 50% of 10, right? It's 5? Yes? Okay. So what we're going to, so where do you think the now this is percentages, right? Because this is a proportion, right? And we're taking number of heads out of 10. So it's a sample proportion problem. So it's percentages. Where do you think the true proportion lies? Right in the middle. At 5 out of 10. So we kind of actually know what the true proportion would be here, but pretend we didn't. Pretend we didn't know. So what we're going to do right now, we're all going to simulate some p-hats on our calculator, which is kind of cool. And it shows you what we're trying to do. It kind of gives you more of like a tangible conclusion here. So here, on this slide, everybody go into your random number generator on the calculator. So that's math. So go into your math menu and then hit probability. You all have to do this. You all need a calculator. Go get a calculator, Zach. Top left drawer. I'm going to do one too. I need you all to do this, okay? All right, now we're going to set the lower to 1 and then the upper to 2. Why are we doing that? Well, we only want 2 options. We want heads or tails, right? Guys, 1 and 2, heads or tails. So we're going to say that getting a 1 represents heads and getting a 2 represents tails. Okay, so I'm going to do this right now because I didn't want to lose this screen, but I'm going to go math, prob, it used to be PRB, rand int 1, 2, and 10. Okay. Now, what did that just output? Right. So now, what does this 2 represent? Tail. Then that represents head, tail, heads, heads, tails, tails, heads, tails, tails. Now I'm interested in the number of heads here. So 1, 2, 3, 4. I got 4 out of 10. Is that kind of, well, that's not that bad. But what does that represent? That represents what? Is that the P or the P hat? P hat. What did I press to get to what? You're going to have to do this because everybody's going to record their p hats. So I'm going to put my p hat up here. I didn't hit enter 10 times. I just did 10. Like this is saying hit enter 10 times. You don't have to do that. If you just say output 10 numbers, then you don't have to do that. All right. So there's my p hat. All right. We're going around the room. How do you type what in? Look. Math. I'll do another one, and I'll record another p hat. Probability, rand int, 1. Okay, now let's do this one. We'll just do another p hat. 1, 2, 3, 4, 5, 6, 7. Okay, 7. So there's another p hat. All right, Lily, come up. You're on deck, Zach. Let's go. We're going to do this quick. Quick. So you place your p hat. All right, come on, Ark. Lily, come on up. Just make a line. Put your p hats. You got 9? Really? Wow. You really did get 9? You got 8? Do another one. Good. You didn't do it? Why? All right. All right. Did you?
Yes.
For real? You got 1. All right, but nobody got 0 and nobody got 10.
I'm trying.
Okay, now listen, because I want to wrap this up.
Hey, it's 9.
Okay, so a 9. All right. So do you see how if I kept sampling after sampling after sampling, I would get a curve that looks pretty much exactly normal? Yes, guys. Okay. Now, these are all p hats. Okay. So what is it attempting to do? It's attempting to show you where the true proportion would lie. We already know it would have been 5. Now, this is where the statistical inference comes in. If you had a coin and you got 10 out of 10, is that likely to happen or unlikely to happen? Very unlikely, extremely unlikely. Nobody did it. Nobody got 10 out of 10. So if we actually put up the margin of 2 standard deviations, 10 out of 10 would lie outside of 2 standard deviations. So this would be unlikely. This would be unlikely. Whoops. And whatever in here is likely within 2 standard deviations. Okay, so now one more conclusion. Could you possibly question if the coin is fair?
Yes.
You can question it because how many simulations did we do? And in my other class, none of us got 10 out of 10. So you've heard of a biased coin before, right?
Yeah.
Where one weighs more on one side than the other, and then therefore happens to, yeah. So this is where we're headed. So the only homework tonight is to start Delta Math, okay? We're going to dive into the blue packet. I know today was a lot of notes and a lot of theory. Hopefully you stayed with me. And the review book is due tomorrow. Well, then you better have it by Monday. It's $3 in the main office. We're going to start reviewing on Tuesday, okay? So thank you guys for being good. Say hi to everybody that took the AP World. Wish them luck. Well, I guess I should have wished. Well, I would have wished you. I did wish you luck, period 1, but it didn't record. Bye. Bye. How come you didn't do it? What the p hat is? Okay, hold on.